All right, let's jump right into a topic that is absolutely fundamental to how we experience reality, but it's something we almost never actually stop and think about. We're going to explore how we perceive the world in 3 dimensions.
This right here, this is the big question. It's the central puzzle of what we call depth perception. Think about it. Your retinas at the back of your eyes, they capture the world in 2D, just like a camera film. Yet you and I, we see a world with depth and distance and space. It's a trick our brain handles so seamlessly that it just feels automatic. But how does it really do it? So here's our game plan for today. We're going to start with that big puzzle of 3D vision. Then we'll get into the mechanics of how our eyes work together. After that, we'll walk through a classic psychology experiment to see this stuff in action. We'll break down the data, and finally, we'll connect it all back to why this is so critical in our everyday lives. Okay, first up, let's tackle this puzzle of 3D vision. Before we can really get into the nuts and bolts of the experiment, we need to set the stage and define exactly what we're talking about when we say depth perception. You see, depth perception isn't just seeing, it's judging. It's your brain's incredible, and I mean incredible ability to interpret the raw data your eyes are sending it, to figure out how close or how far away things are. This is absolutely essential for, well, everything, from catching a football to just walking down the street without bumping into people.
So how does the brain actually pull off this amazing feat? Well, it's not just one little trick. It's got a whole toolbox of visual cues it can use. And these cues basically fall into 2 main categories.
Our brain is it's incredibly resourceful. It can actually get a decent sense of depth using just one eye. We call these monocular cues. Think about a painting. Objects that are drawn smaller or higher up on the canvas seem farther away, right? That's your brain using monocular cues. But the real magic, the high-definition, super accurate 3D vision, that happens with binocular vision. By comparing the slightly different image from each of your 2 eyes, the brain calculates depth with stunning precision. And that is the core question of the experiment we're about to look at.
See, in psychology, we don't just stop at how does it work, we have to test it, we have to measure it. So let's walk through how a really simple but honestly elegant lab experiment can physically measure the difference in accuracy between one-eyed and 2-eyed vision. Every good experiment starts with a hypothesis, a clear, testable statement. And this is ours. We're basically predicting that using 2 eyes is measurably better, in other words, more accurate, than using just one when you're judging depth. Now that might seem obvious, but science is all about proving what we think we know. So how do we test this? Well, the setup is simple. A participant, in this case a 24-year-old graduate student, looks at 2 stationary rods and a 3rd rod that moves. Their only job is to say stop the moment they think the moving rod is perfectly aligned with the other 2. We simply measure their error in millimeters under 4 different conditions, using one eye as the rod comes towards them, one eye as it goes away, and then we do it all over again with both eyes open. Simple as that. All right, the experiment is done. And now for the really exciting part. Let's look at the results. Did the data actually back up our hypothesis? What did the numbers have to say? Okay, so here's the raw data from the 10 trials in each of our 4 conditions. Now these numbers are the error in millimeters for every single judgment. And I know looking at a table full of numbers can be a little much, so let's just focus on the most important part, the mean or the average error for each condition, which you can see highlighted right there at the bottom. And this is where it all becomes crystal clear. We've taken the averages for all the one-eye trials and all the 2-eye trials and put them on a simple bar chart. And wow, the difference is it's stark. Look at that. The average error when using just one eye was almost 2 millimeters, but the error when using both eyes, well under 1 millimeter. And here's the key takeaway. It's really simple. The smaller the bar, the lower the error, which means the higher the accuracy. The participant was significantly more accurate. We're talking almost 3 times more accurate when they used both eyes. The data couldn't be clearer. Our hypothesis is accepted. Okay, so we've proved it in a lab with some rods, but why should we care about a couple of millimeters of error? Well, it turns out those millimeters matter a lot when you step outside the lab and into the real world. This isn't just some abstract academic exercise. That amazing accuracy you get from binocular vision, that's what allows you to drive a car and perfectly judge the distance to the brake lights in front of you. It's what allows a surgeon to operate with micrometer precision. It's what allows an athlete to catch a fast-moving ball, and what allows you to simply walk down a flight of stairs without tripping. Our entire seamless interaction with the world around us is built on this foundation. And this illustrates one of the coolest and most fundamental lessons in all of psychology. What feels like you're just passively watching the world is actually an active, nonstop process of construction that's happening inside your brain. Your reality is literally being built moment by moment. So I'll leave you with this final thought to chew on. If your brain is working this hard to build something as basic as 3D space, what else is it building that you completely and totally take for granted?